So like I said, I brought my own brain today. So we're very, very proud of this. That took me like 30 minutes to put this thing together in the car. So I'm Daniel Yates. I have an associate's in physics, a bachelor's in polymer chemistry focused on medical tech. I studied how to target cancer cells, Zika, Ebola. I've always wanted to go into quantum mechanics or neuroscience. So I have studied neuroscience of people. I actually have studies in nonverbal human communication in actual college. So I transferred that over to reptiles because people have been doing this way longer than me, and I've still been able to teach them. So today, this is what we're doing. This is a rainbow from the Mandula. That's how I figured that out. So this is a bearded dragon's brain from an MRI. So we have the red spots are the actual forebrain. There's no way I'm ever going to tell you to be able to pronounce that. I'm a math major for a reason. But the forebrain holds their imagination, their memory retrieval, their decision making, and more. Well, this tube in front is your OL stalk. It stands for oral factory stalk. And then this orange is your thalamus. It connects all the parts. The pink or purple or whatever this is your actual optic nerve. It sits under their brain instead of in their eyes. This is why they're able to get that 260 view. And so then so there's two hemispheres, just like people. So this is your optic tactum. This is where your sight and your ears are dissected. Whereas your OL stalk, that's your smells and your taste are dissected in your brain. And so then we have the medulla, which is the nervous system. It's what travels and sends a signal down from your spine, connects the spine to the brain. And then you have your cerebellum, which is your motor functions and rehabilitation. Actually, like regrowing limbs would probably come from that as well. So this is our great ancestors. Is what they think is it. I know it looks like a Langolier from Stephen King, but this is what they believe. If you go far enough back in history, what every vertebrate has as a common ancestor. So our brains actually come from the same source. So something I love teaching, blind sight. Blind sight is when your eyes work, but your cerebral cortexes in the back of your brain do not. Well, one thing that they actually found from this, because that cerebral cortex takes up so much power in sight, that it drops off information in your optic tactum. So this actually has a pathway, and it always crosses hemispheres. There is no study to ever show that any vertebrate does not change hemispheres. That has never been found. So we can see pathways. So when we look at the bearded dragon brain, what are we thinking of pathways? This is a sphere. So when you think about this, you think about the optic tactum. Are these kidney inside? So your information here goes everywhere and comes back. So it connects both sides of the brain, because one side is your memory retrieval, the other side is your imagination, feed off the same things. Whereas this is not spherical, this is linear. So when we look, we know this goes here, it travels. This is probably one of the most important things that nobody's ever really studied. Nobody has studied this. The thalamus, because that's what connects everything. And so we can see, could you imagine what that information now has to do? So when you go from your optic nerve, optic tactum, like the human being, making decisions in your forebrain, back to your optic tactum, down to your medulla to move your muscles, just to make a decision. So the reptile brain means that it has to have a delay. If they don't have a delay, they were already thinking about it. This is not instantaneous. I've got videos of bearded dragons actually blackbearding and taking a minute to do it. Most people think, what are they doing right now? No, think about what just happened. Because they don't instantaneous. This is why, that pathway. That's so sharks' brains, linear. Whales' brains, spherical. Mammals. Why do sharks bite people? Because they want to see if it's food. Why do your lizard bite you by accident? Because it wants to see if you're food. Because it takes a minute for it to do it. So linear. So there was a study done. This is the only study that I've ever seen that you had 40 reptiles in this. So this is where most of my information comes from, but I went above and beyond what they did by my understanding of vertebrates brains, from studying human brains, understanding how that works and transferring over what I can to this. So your cerebral cortex, your cerebellum is actually, you can see snakes and limbless actually often move away from the optic tectum. And they're often thinner because they don't have limbs. And like I said, this controls your motor functions. Whereas ones that are toroidal, testicular, and cerebral, well, they will actually wrap over the optic tectum. So this is a way of identifying and understanding if it's a snake or a legless lizard or something that buries itself. If it buries itself, it's going to have a bigger one. It's going to have thicker. And it's going to go over that if it actually has 4 limbs. If it doesn't, it's going to go backwards. And so that's what this is doing. This is not forward. Imagine the optic tectum is on this side of the brain, on this side of your tongue. So you can kind of see where it's going. And that is what they found. They found 5 your legless, limbless that are burials, and then you have your arboreal, the arboreal 4-legged quadruped, and then there's the. I'm a scientist, not a biologist. I'm not great with names, but the tutorial, and then both, where it does both. Now, medulla is something I have. Like this, when we look at this, it's really fascinating. And so we have the rainbow boa, we can see, so that was a ball python. Does that look bigger than this, the medulla? This part of it? It actually does. You actually see this seems to keep more than this does. When our brains, when you see the wrinkle, it's because we're actually using more information, and so it wrinkles to create more surface area. This has nowhere to go, so it peaks. But you can see that overstimulation. So flying lizard versus flying snake. This guy has stretched his skin, so he has an oversensation in his tactile nature. His medulla comes actually further down than his cerebellum. This cerebellum pushes this down, but this doesn't come down on its own. So this is actually bigger medulla than that, the way it's actually kinky. And the reason for that, he stretched his skin, while his skin is just flabby. So he doesn't have, this is where I came into, I want to test ball pythons versus rainbow boas to see if they have a better tactile. See which one's based off this. I don't know. There's so many things left to study. So we need to use vertebrates to prove my point. Which one do you think is the flying squirrel, or which one's the gray squirrel brain? A is the flying squirrel, has the longer medulla because it stretched its skin, so it's over tactilization. This is how we prove the points here. Because when you put them in an MRI, you can't get what you can in a human because you have to sedate them. So when you look at a brain, almost every part has multiple functions. So when you look at this brain, you will see the different colorizations based on multiple different functionalities in their brain. We can't do that for them. That's where it limits. So we just have to kind of play with it and see what actually comes about. That's where that, but we do know that is where it should be in the brain. If it's not, then it changes our whole look of evolution. So, the optic tactum, this is the bread and butter. So when you think of modeling, when I yawn and you yawn, blind sight people still do this because that's where your cerebral cortex or where your cerebral cortex is damaged. But right here in that optic tactum for a human is your actual modeling part of your brain. They have the same thing. If they see something running in the woods and they're fearful because they need to be. So it's actually a evolution trait from this. So they may or may not have empathy like we do, but they have that modeling part of empathy. They have to. And so it's really fascinating. But because we know that all these parts do different things, and there's cross hemispheres as well, the tokay gecko out of that study, they did not have a 4D model of his brain. But I looked at the numbers and I compared it to a bearded dragon and a day gecko. Day gecko was like 80-some thousand. Bearded dragon was not low 90-some thousands. The tokay gecko was 80-some thousands until all of a sudden one spot was 4,000. What does that tell us about their optic tactum? That tells us it's not the same shape as the bearded dragon or day gecko's optic tactum. So that tells us one of these parts is not used because your brain is a muscle. You use it or you lose it. You use it, it grows. If you don't use it, it fades away. So something in their optic tactum fade away. We do not know what that is. But that's what that tells us. And this is why, when you're dealing with the tokay gecko, you go in low and slow because it's scared, because it can't dissect the information as fast.
Is this same behavior trait, does this allow them, or rather impact them when it comes to mirroring behaviors they sense from other creatures?
Oh my God, I had some emerald swifts, and they're both sitting like this. I accidentally scared this one. This one jumped identical to the way this one jumped. So it does that, and so it should impact. But then when they need to make a decision, that thing would have to come out of here and go up here. But imagine when they get that fear, it goes straight to the medulla and moves their muscle. So it's what we would call instinct. So when they refer to reptile brains, this is actually what they're talking about.
Yeah.
They're just the optic tactum and the medulla, or the midbrain and the hindbrain. They're not talking about the whole reptile brain. If they don't know that they're not talking about it, they don't understand that.
So basically they react faster with emotion rather than thinking about what's happening in their environment.
Yes. That's why there's delay in their decision making. Yep. So, the bearded dragon, third eye. Me and Ryan McVeigh, we had a talk once, and he said this thing can see the different spectrums. I said, no, there's no way a scale is going to pick up on that, because for that, imagine how big your eyes are to do that. Why would a single dot transfer that much information? Because it would actually have to travel from where it's at over the forebrains and into the optic nerve to get that. That amount of information is not going to travel that far. It's not. So what it does, it drops down and goes back into the optic tactum. That tactum. And so it actually just moves that way. Really fascinating. And you can see, like, it's just a drop down. And so that makes sense. So when we're dealing with python, the boa's actual labia heat pits, they're scales. They've got the full mustache scale, I always call it. And it goes back to the optic. You can see it stops right here. So this has more than enough space for it to travel here and get into their optic tactum or to make decisions based off of their nervous system. That's where it would be dissected. So when we look at vipers, the labial, it's two membranes sitting right here in the front of their faces. So if there's just two simple membranes, It's 10 times faster than a Python, and it's like 0.02 accurate. How is that information able to travel from a membrane in the front of their face to their optic? That's not going to be possible, especially for it being that fast. It goes through their medulla. It's actually a muscle. And we know from just what we said here, how fast it travels from the optic tactum to the medulla instantaneously, basically. Goes the opposite way, instantaneously, basically. That's how they get to go so fast. That's the difference. I love that. That was, to me, figuring this out was a huge highlight because I had this question for months. So the thalamus, nobody's ever studied. So we know thin layer for humans. So what if this thing actually had more thalamus between these two? Would that not change how they behave? Because there's faster communication between the two? Well, as we can see, it doesn't. So it's really fascinating. We'll get back to that. So this is something that isn't studied. I've never seen a study on this. So the OL stop, the oral olfactory stop. So the Jacob organs attached to this. The smell, their taste, everything. The quick tongue flick is just a reinforcement of what they see. So that's why lizards and everybody do it. I see it. Is it what I see? So then it goes through here, and this always attaches to the actual forebrain. So when you smell something, oh, I smell, pecan pie, Thanksgiving, immediately you think of a Thanksgiving because it attaches straight to the thing that has your memories. So if you go straight to your memories, imagine what a T-Rex went through, having that big mouth opening and having something sucked into the mouth, all that air, that information, and all of a sudden, this Triceratops tastes like something my mama killed for me. Like that's exactly what it would do. Like it's not something most people think about, but we can see the difference in size. Bearded dragon, about 10 to 15% of their brain mass is OL stop. We are 1%. And think about how strong that is. So I don't know the percentage for the vipers, but you're looking at 30 plus for snakes. Skinks and monitors, you're looking about 20 to 25%. Kicker is, most of us would say that skinks and monitors are smarter than most other reptiles. So, the forebrain are decision makers. So, like I said, we don't understand this in their brain. We do not have the technology to do this, but it's there. They should have every piece of this regulation in their brain for memory and so on. So every vertebrate crosses hemispheres. Your imagination is in your right hemisphere. Your memory retrieval is in your left hemisphere. So your eyes will dart to the right when you want to remember. Your eyes will dart to the left if you want to imagine. It's really fascinating. But when we look here, the beardy looks like a hump. It's the first hump in 3 humps when you talk about it as a linear. The viper's different. The snake is even different. But the skinks, I don't have a model of a monitor, but this is probably the same. This is probably the reason why these are probably more intelligent. That brain looks like, instead of just a bubble, it's stretching parts of its brain because of that OL stop. So therefore, that's like 2 peanuts together or like 2 jelly beans. So that information, because when we think of creativity, most people want to go, well, you're making art, you're doing this. No, creativity is the combination between your memory and your imagination. So if that's the case, this is quicker and probably more functional to be creative because of that stretching of the brain, how it stretches. So, but snakes are 30%. So why don't they have like that more? Because their OL, their optic tactum is smaller, and so it creates this long shape. So whatever's in these corners is harder to get to the other side. That information takes longer. So it doesn't mean it doesn't have it. So it doesn't mean these things are actually less intelligent than a skink. It means it takes longer for that information to travel and do things. So that's why I always explain skinks and monitors have more information coming in than other reptiles, but they have a way to transfer it faster. That's what makes them intelligent. It's not because the other guys don't have the ability. But look at the viper brain. It's like 2 Pop-Tarts, like it's stretched out. So imagine what's on these corners. I have no idea, but whatever it is, takes even longer than a boa or a python to get to the other side. So how would this affect? So this makes me wonder if this impacts the fact that they are, they are ambush predators. So does it take less imagination to be an ambush predator than something that has to actually stalk its prey, crinkle it, stretch it, kill it, and eat it, kind of thing? To just imagine something walking by and striking at it? I guess it takes less, maybe. But it's very fascinating. But what came first, this or the ambushing? Which is really fascinating. And I think that really opens up so much information on what we know, how like you can define intelligence. So I said the crosses hemispheres. So this is trap talks monitors. So this thing's been held quite a few times. It sees something in the room. So it's actually being held. It goes right. So what did we say? Right is memory. So it's remember it being held. So it moved to its imagination. Yeah. So this thing went from its memory to its imagination. It had no reason to stretch its brain head like that. So it saw something and went, what is that? Really fascinating. I watched a lychee gecko at NRBC one year, helping US Art, and the thing literally went around in a clockwise circle on the table. And I'm in my head going, why is this like, it's in a ballroom full of people screaming. Why is this a memory for this thing? Like that's insane to think that this is a memory. So the tongue flicks. So we can see this tongue flick up. So the tongue flick up is memory. The tongue flick down is actually imagination. So it's not just like, oh, it was like this. No, it's this. Like it's down. This is up. Like you can see it in this. He's put it away, and you can see the tongue flick down. He's trying to explore. He's trying to figure things out. The curtain, I guess maybe it's not going to show it here. Maybe it's cut off a little bit. It's fine. But he tongue flicked that and went up. He remembers the curtain. And he also, when he moves towards him, he went up. So like he remembers him. I watched the guy at the show hold a corn snake, and that's what he did. Now, imagine being creative. So using both parts of your brain. That's what this is. The more it does this, it's actually being creative. So it's just using its imagination and memory at the same time. So when you see your tagu or monitor do this, it's using both sides of its brain.
Is that because of the bilateral stimulation?
Yep. It's just like when your eyes move back and forth. And I can never remember what up and down is, but it's something with your eyes as well. I just can never remember what it is. So this is really fascinating when you look at this. Just the strokes. Like I said, the singular tongue flick is just what I'm just reinforcing what I see. That's all it means. Oh, I see this. Oh, I remember this. Yeah. Oh, so now I'm a scientist. So what scientists do is we have to take our theories and we have to make sure they're able to be disproven. If you cannot have a method of disproving your own theory, it is not an actual accurate scientific theory. So theory, the size of the forebrain correlates with the size of the territory of that individual animal. Makes sense. It's where its memory lies. Perfect sense. So I wanted to find the animal with the biggest territory. So we can see how this matches. So what has the bigger territory? This is the territory of the leatherback sea turtle. Like that, yeah, there's nothing with a bigger territory than that. But we can see this is a Japanese study. So this is the leatherback. This is the second biggest territory. I can't remember what this is. But all these guys live in the shallows. They have the 3 humps like a regular reptile brain does. They live in the shallows, and they have friggin' actual things to map. They're actual, so imagine coral. So they have coral to map their territory. All reptiles, I said all reptiles map their territory. This is why when we go into, when I make sure that when I talk to kids and stuff, when you move a rock, you move it back. Because they've memorized how that looks. This is a fact. So, we can see this looks normal. Well, why does this look like a pile of poop? Why? Because it lives in a deep, dark ocean. There's nothing to map. That's how much of your brain power is used for sight. So this is basically a blind species. His eyes, look at his eyes, comparatively. So much smaller than the others. But yet that shows you how much brain power you actually need to truly function. So blind species, pretty much flat, because their optic tactile isn't very big. This is basically just doing sound. It's really fascinating. And I mean, it's just wild. Their OL stock's huge, and it just floats into everything. Just looks like a flat field. It's really fast. They got every piece, but your optic tactile is really, really tiny and just goes straight into the mandibular base. So it's basically non-existent. I hated this study because the way they talked about their mandula or their optic tactile was basically like the same size as a regular one. And it's like, no, we can see that. But yet, the way they 4D model it, it doesn't look that way from the numbers. So the numbers are a little misleading, so that's why I'm very curious. I didn't love the study, and I don't take it as full value, just with the cerebellum. Because we know this, because this is vertebrates. This is probably what most blind vertebrates look like. It would be very curious to see what mammals look like when they're blind. So what kind of brain is this? Probably a good thing from the eyes. But the eyes, I mean, it has an OL stalk like a beardy, has a hump like a beardy, has optic tactile like a beardy. I can't tell if that's going forward or backward. I think it's going forward. So yeah, the mandula is not very big. So it's not a species that buries itself. So it's not something that's over tactile sensation. And it's arboreal, most likely. And so yeah, it's a veiled chameleon. This is my this video. This is Piscio man. He's at least 6 veiled chameleon. I'm doing hospice for him right now. Doesn't he look like a Muppet? I know he doesn't look the greatest. Like I said, he's at least 6, at least. And they only live to be about 7 or 9. Yeah. And so what is this? So you can see the mandula is not that big. So it's not a species that truly buries itself, but yet it's not tiny either. So this is kind of going this way. You can see here it's actually going over. So it's a 4-lived. And so then we can see basically a same mandula or a optic tactile way it's set up. This is a Uromastix. I don't love the hand drawing stuff, but it's still something to look at, something to know. And so she recently passed. Yeah, those. So this is a huge question that I have. This is 15 centimeters long. The Cape dwarf chameleon gives live birth. Fascinating. I wanted to put a video of this, but Jackson chameleon. Brain's the same size. 25 centimeters or 30 centimeters, 15 centimeters. I have no idea why. This is the one chameleon species that I want, but it's CITES. You cannot own it without a CITES permit.
Why is it endangered?
Yeah, Madagascar. So, but their brain size is exactly the same. I have no idea why. Now, any questions?
Has there been any studies on the brains of spitting cobras and how that might relate to the intelligence of their brain
no.
size?
Not as far as I know.
What are brains of land turtles?
Brains of what?
Land turtles, like tortoises, box turtles.
I didn't see a lot of those. The limit on the type of studies, I have never seen a monitor brain. That study with the 4 of them, they didn't even have a blue tongue skink. Like they literally had 40 species and they didn't have a.
Between a brain of a water turtle and a land turtle.
There shouldn't be any. There really shouldn't, because it's the same principles. So it's okay. So this thing's not burrowing. So the mandula is probably. One thing about geckos, because of the tactile sensation, maybe their mandulas are longer. No, they're not.
Now, how do you tell if you have a pet, how do you tell if it's happy or not? How do you tell? How do you know if it's happy?
That's a very interesting question, and you'll get 50 different answers. My thing is just how comfortable it is, because it can never be happy if it's never truly comfortable. But also, how does it know it's happy if it's never known problems either?
Stress or no stress?
Yeah, it's like,
And is the brain different? Is the brain different from a harmless snake to a venomous snake?
yes, actually. Yeah, we saw see how it's shaped? That's the forebrain. See the shape of python? Boa? That forebrain, that's your decision making, your imagination. Completely different shapes. So that would absolutely have an impact on how it behaves and thinks. Now, all of this needs more study. Everything here needs absolutely more study. Like I said, nobody's ever studied that mandula or the thalamus. So my imagination is leading me to wonder, when we look at the thalamus here, imagine what it might be for a monitor. That it might actually have, like it might actually travel further up, allowing it to have more information. When we look at these forebrains, I don't fully understand this one yet. Why does this forebrain come down and these don't? I don't know that. I haven't figured that out. But it's very fascinating. So does this change how that thalamus sits in there? Because like I said, here, we can see there's not as much light here, or shadow, as there is here. So maybe there's more information being passed in the fiber scheme between these two hemispheres. And that's why the skinks are actually more intelligent, because they have more information and more information able to travel faster because of that thalamus. I think that thalamus is the key to most of this stuff, and it had never been studied.
And how do you figure out if you're a threat or not a threat? Is that a good example?
So what I like to do, so you have slow blinks, you have things like that, holding it over your head, things like that, because it's programmed into their optic tactile. That's what the modeling part is for. When they see other things scared, they know it needs to be scared. They don't need to stick their tongue out and figure out if they need to be scared. They already saw it. They know it's there. They know they need to do something, and it automatically moves down. So that's instinct. It's like when you see people, so they've done plenty of studies where they've had like people run around a corner and the guy run with them. That's the same principle. It's the same part of the brain working. And it's just, so for me, what I've always taught when it comes to nonverbals, don't ever stand in doorways when you're talking to somebody. Allow them an exit so they can be more comfortable. Stand beside them. So when I seen video of me handling my skinks and stuff, this is what I'm doing. And I'm holding it from underneath. Clint's Reptiles finally figured this out. I've been doing this for 3 years. He's talked about it finally, like, oh, well, snapping turtles, when you just pick them up like this and you're supporting all 4 limbs, they don't bite you. It's like, oh, they don't see you, like you're threatening them, so they don't bite you. Like, it's really wild. I'm like, I've been saying this for 3 years, but I have studies in nonverbal for vertebrates, and all vertebrates are going to see that. But just because of the experience of the animal, things like that, this is why the wild caught, they often talk about the, what type of skink is that? The emerald green tree skink. The captive bred are so much more wanting to interact with you and play with you. Which probably goes back to this. So the difference between probably an oscillating skink and a emerald green tree skink brain, the mandula. So when you want to think about intelligence, is another way to think about it. If you take this whole brain and just call it 100%, then you think the more it's actually spread out through the brain, the percentages, the more intelligent the animal. So the more that the mandula, because we would see a oscillating skink is less intelligent than a captive bred emerald green tree skink. Well, the only difference in the brain is probably that mandula. It's taking up more energy. So it's really fascinating when you look at it like that. But it's just literally doing what you would do with a human. Imagine how you would want a human not to fear you.
Yeah, how smart, I have a wood turtle and spotted turtles are very smart. In what way?
I have no idea.
Because they're very intelligent.
Oh, yeah.
And
Like I said,
they're more intelligent than a box turtle or a tortoise, something like that.
I am curious about Otis.
How smart are they?
Otis from Garden State Tortoise. Like, he's supposed to be one of the most intelligent tortoises they've ever had. He acts like a dog, like a little kid. Whereas all the rest of the what is he? A spotted turtle? Otis from Garden State Tortoise. He's very, like, if you ever see it, like it's yeah. So I'm just imagining, because they've recently did a study that they've published on snakes, and they found the midbrain and hindbrain, the optic tactum and medulla, when they gave them enrichment, according to Tubbs, the enrichment ones actually had larger. But once again, it's not because, I'm going to make this very clear, it's not because they have more neurons. It's because the pathways were grown, and so like the myelin between the stuff grew because of the enrichment. This is what happened to Einstein's brain. This is why Einstein had a bigger brain. Just like a muscle. It really is. And you create pathways, and myelin wraps those pathways, making them faster. That's what happened to those snakes. That's why those brains were bigger.
Okay, time for one more question. He's going to be here after our meeting, so one more question.
Okay, I'm gonna go back to the turtles real quick with sea turtles. So we've seen for sure that there's definitely a correlation, like if it's blind, its brain's gonna be generally more flat. But what if specifically sea turtle, what if part of the reason it doesn't need sight is because it's deeper in the ocean, close to where gravity's like crushing it, so it has to be flat to get that adaptation?
No.
Okay.
Because otherwise, this is actually one species that also travels those waters.
Okay.
It just spends most of its time in the shallows. But it has the second biggest, because it does do that same thing.
Okay.
And it still come on land to lay eggs.
Yeah. Like this thing still does it too.
Yeah.
Yeah, like it's still, yeah. And it's really fascinating, because everybody gets on to me about the memory stuff, because DNA does hold memory. But is it like a computer system where it's ones and zeros, so your DNA is making your RNA, so then you create your next cells? Or is it actually able to pass memory? Because I didn't even get into the forebrain stuff, that why this doesn't wrinkle yet. That's a whole different topic, a whole nother set of things to talk about.
We'll invite David back to solve that answer.
Yeah, that's a,
Thank you for your presentation. Thank you.
Here we go.
Yeah.
Hold on. One thing Daniel gave me is a bunch